Good morning, students. In this video, we'll discuss about the logarithmic amplifier. The main intention of the logarithmic amplifier is to show the output of an amplifier in terms of the log. To show the output of an amplifier in terms of the log. For example, till now we have seen the different types of amplifiers like instrumentation amplifier and other amplifiers of amps you would have used in case of the amplification process, as well as in our filters also we have seen the amplifiers. We have used the operation amplifier, but those amplifiers outputs are represented either in terms of the current or in terms of the voltage. But till now we have not seen the output of a particular amplifier in terms of the log. So in order to show the output in terms of the log format, we are using the logarithmic amplifier. So the logarithmic amplifiers are the amplifiers only, but they are representing the output in terms of the log. Now the question comes at, do we need any special element to represent the output in terms of the log? To represent the output of an amplifier in terms of the log is a question. So till now you would have studied so many basic components in the electronics like resistor, capacitor, inductor, diode, BJT, bipolar junction transistor, FET, all those things. Now the question is, which device is more useful for us to view the output in terms of the log format is a question. So if you are aware of the diode, there is a normal PN junction diode. You would have seen the formulas in terms of the log, like current passing through the diode and output voltage of the diode. All those things here are somewhere you would have seen that those equations are in the form of the log format. So here the main intention is, whatever the amplifier we are designing as a logarithmic amplifier, we are going to make use of the diode. We'll make use of the diode to give the output of the amplifier in terms of the log format. Let us see that particular circuit diagram. So here if you see on the screen, wait a minute. If you see on the screen, this is a logarithmic amplifier. This is a best example for the logarithmic amplifier, which is designed using the PN junction diode. So I am connecting the PN junction diode in the feedback path and in the feedback path of the operation amplifier, and output will be there in terms of the log format. We will see that one, how exactly we will get the output in terms of the log. As we move on, we will see. In general, we can make use of the diode to give the output in terms of the log, but there is a drawback for the diode. It purely depends on your interest whether your amplifier which is designed as a logarithmic amplifier should be worked for a long period of time or short period of time. Like if you would like to make use of the logarithmic amplifier for 4 decades or 5 decades, then you can't use the diode for giving the logarithmic output, because the diodes are not giving the proper characteristics for long period of time. They are giving the logarithmic characteristics and the proper characteristics for 1 or 2 decades only. So if you want to make use of the logarithmic diode for long period of time, like 4 to 5 decades, then you can't use the diode for your logarithmic amplifier. We will come to that point, but let us see what exactly what is happening when we are using the diode in the feedback path. To get the output of the amplifier in terms of the log. So as you know that, if you see on the screen, on the screen you are having the operational amplifier which is connected with input current IN. So I am assuming the input current is IN. IN current is applied to this particular one, and the diode is connected in the feedback path. Okay. Let us suppose the diode is in the forward bias. So obviously there is a current passing through this particular diode. That is indicated over here. So the current passing through the diode, I am assuming it as a I, which is displayed on the screen. Okay. So I. So how much current is passing through this particular diode? The same current comes to this particular junction. But as we know that at the junction the current will get split. Okay. So means some current should go in this way and some current should go in this way. But as we know that the ideal characteristics of the operation amplifier says that the input impedance of the operation amplifier is infinite. Infinite means it is just like an open circuit. Because of that, there is no current passing through this particular terminal. Means there is no current passing into the non-inverting terminal of the op amp. Instead of that, the current, whatever the current which is passing through this particular diode, that will be appeared at the input also. Okay, means what I mean to say that at the junction we are having the split, but due to the high input impedance of the op amp, the current is not entering into the inverting terminal of the op amp. So the current will be appear over here. Means how much current is passing through the diode, same current will be the I in current. Same current will be the I in current. Okay, but we know the formula for the current passing through the diode is means we know the formula for current passing through the diode. I'm not here to derive all the things, but I'm taking the equation directly. Means the current passing through the diode. What is the equation? What is the current equation which is passing through the diode? Okay, so for that the equation is this one. If you see this one, the current passing through the diode, which we call it as a diode equation, so is I equals to the I naught into e to the power of qv by kt minus 1. qv by kt minus 1. I is nothing but the current passing through the diode, and I naught is nothing but the reverse saturation current. As we know that the minority charge carriers also playing a major role in current passing through the diode. Okay, but we are not going for what is that PN junction diode and depletion region, all those explanation we are not going. We are simply taking the current passing through the diode. The terms which are there in this particular equation are I naught. I naught is nothing but the reverse saturation current, which is due to the minority charge carriers, and the E equals to the Q is nothing but the charge of the electron, that is the electron charge, and V is nothing but the V value will get changed depending on the material which is used in designing the diode. We may use the silicon material or we may use the germanium material in designing the diode. So depending on the specific material, the value of the V will get changed. So that is nothing but it may be the 0.3 volts or it may be the 0.7 volts. It purely depends on which type of material you are using for designing your diode. And K is nothing but the Boltzmann constant. T is nothing but the absolute temperature. T is nothing but the absolute temperature which is there on the screen. Okay. So this is the equation number 1. I am assuming it as the equation number 1. What is my intention? I would like to get the output of an amplifier in terms of the log. So later on we will go for explanation, means we will elaborate our explanation in such a way that instead of using the diodes we will go with the BJT. Why we are going with the BJT? I will come to that point. But just remember that this is the equation for current passing through the diode. Now let's see in the next slide. So if you see this one here from the equation number 1. Equation number 1, as I told you that how much current is passing through this particular diode, the same current will be appear at this particular point. Means In equals to the I. So I am rewriting the equation number 1 in terms of In equals to the I naught into e to the power of qv by kt minus 1. So if you do some mathematical calculations like bringing this one to the downstairs, means instead of taking the I am just taking the what is that in. Okay, an in term. Okay, so In by I naught equals to the E into e power qv by kt. So after some mathematical calculation, means if you bring this exponential to the left side, as you know that it will become the log. Okay, so I'm just taking the log natural. So qv by kt equals to the log natural In by I naught. So if you rewrite this one, V equals to the kt by q into log natural In by I naught. So this is the equation for what? It is a voltage drop across the positive and negative anode and cathode of our diode. So if you are going to the ideal characteristics, this value is a 0.3 or 0.7. That purely depends on the type of the material which is used in designing the diode. Okay, so this voltage is nothing in ideal characteristics. A particular diode, as you know that, I hope you know this one. In ideal characteristics, if a particular diode is in the forward bias, I think I have to take in the reverse, right? Wait a minute. If you take the ideal characteristics, I'm just taking this is my diode. I'm having the anode as well as the cathode. So if you are talking about the ideal characteristics, in general, ideal characteristics of the diode in forward bias is in general, for the basic explanation we used to take it as a short circuit. But if you want a more practical one, then during the forward bias of this particular diode, when the diode is in the forward bias, it will be replaced with the voltage. That is called as the knee voltage or the breakdown voltage. So this V is indicating the knee voltage or the breakdown voltage of our diode. Means this one, whatever the positive terminal we are having. So this is a negative terminal of the diode and it is a positive terminal of the diode. Positive terminal is connected to the means we can replace this particular diode with this one, with this particular voltage symbol, because it is in the forward bias. It is in the forward bias. So this positive means this terminal is a positive now. This terminal is a positive now. This terminal is a positive means the same voltage. How much voltage is there at this point? The same voltage is there at this point, as well as the same voltage is there at this point. At this point. So this voltage is nothing but what? It is a voltage at the output terminal of our operational amplifier. So that's why I'm rewriting this equation in terms of E naught equals to, means when we are applying the current I into the operation amplifier to this particular circuit, the output voltage E naught is equals to the V equals to KT by Q, means this output voltage is nothing but this voltage only. I'm sorry. This output voltage is nothing but the output voltage at the operational amplifier is nothing but this voltage only. So I'm rewriting this equation in terms of E naught equals to the V equals to the KT by Q log natural I in by I naught. So I'm assuming this one is the equation number 2. But we have a drawback. So means if you see this one, you are able to get the output voltage in terms of the log. You are able to get the output voltage in terms of the log. Whatever the output we are having, we can see that output in terms of the log. Okay, log. But the drawback of using the diode, this particular equation, because of what? This particular equation because of the diode which is used in the feedback path. But as I told you that the diode cannot give the the specific characteristics for long period of time. Means after 1 or 2 decades, it is unable to give the proper characteristics. Okay, now what we are expecting practically. So it is not going to give that kind of characteristics. To avoid that particular problem, what we are doing is, instead of using the diode, I am going to make use of my BJT. I am going to use the BJT as a diode. So the BJT lifetime means the BJT is giving the required characteristics for a period of 5 to 6 decades. Okay, now so that is the advantage of using the diode, using the BJT. Now the question is how we could make use of the BJT as a diode is a question. Okay, so if I'm not wrong, all of you know the symbol for the BJT, right? All of you know the symbol for the BJT. So this is a symbol for BJT, right? I'm sorry, the diagram is not looking good. So this is a BJT, right? So if you are shorting the collector terminal, we call this one as a collector, this one as a emitter, as we know, and this one is called as a base. This term is called as a base. So if I'm shorting the base and collector, then what will happen? If I'm shorting the base and collector, then what will happen? It is obviously a diode. Means transistor is converted into the diode format by shorting the collector with the base terminal. So here this diode, I think all of you are aware of this one, right? This diode is a whatever the diode we are having. So when you are shorting these two, that is a if I'm assuming this is a base and this is a collector, this is a emitter. If you are shorting these two, then obviously this entire thing will be replaced with one terminal. Okay, so now the BJT is converted into the diode format. So we can convert the BJT into the diode format. That is the PN diode format. It is a PNP transistor. Now whatever the transistor you are seeing on over here, it is a PNP transistor. Okay. So when you are shorting the base and collector terminal, then the BJT, the PNP transistor is converted into the PN junction diode. So as we are converting the BJT in terms of the diode, then this kind of transistor is called as a trans diode. Means the transistor which is translated or converted into the diode format. So because of that one, this particular BJT is called as a trans diode. Because of that shorting, the transistor is converted into the diode na? So that's why it is called as a trans diode. So if you see this particular diagram, wait a minute. If you see this particular diagram, Wait a minute. Unfortunately, I talked that. Okay, if you see this particular diagram, so in this diagram, I'm using the transistor. In this particular diagram, I'm using the transistor instead of the diode. Instead of the diode, I'm using the transistor. What is the use of the diode? Transistor. The transistor is giving the proper characteristics for long period of time compared to the transistor is giving the proper characteristics for long period of time compared to the diode. Okay, compared to the diode. That's why I'm converting the diode transistor into the diode format by shorting the base and collector terminal. If you see this one, as all of us know that, how much voltage is there at the non-inverting terminal input? How much voltage is there at the non-inverting terminal input? The same voltage is there at the inverting terminal. Means it is a virtual ground property. We are having one property called as a virtual ground. Okay, virtual ground in operational amplifier. I'm not here to elaborate the explanation related to the virtual ground. Okay, so virtual ground statement says that how much voltage is there at the non-inverting terminal, same voltage will get appear at the inverting terminal of the op amp. Same voltage will get appear at the inverting terminal of the op amp. So how much voltage is there at the non-inverting terminal? It is a ground. So this ground voltage is there over here. So if you see this one, without knowing to you the base and collector terminal, it is not indicated that base and collector terminals are shorted, but actually they are shorted. How much voltage is there at the collector? Same voltage is there at the base terminal, na? Means it is a ground only, na? So collector is connected to the ground, base is also connected to the ground, obviously it is a shorted. So this diode is acting as a trans diode. Now this particular diode is acting as a trans diode. So when you are taking the trans diode, we are having the equation for the current passing through the BJT. We are having the equation for the current passing through the BJT, which is nothing but the collector current. The equation for that particular one means the current passing through the collector terminal of the transistor. Collector terminal of the transistor is this is the equation. Equation number 3 is indicating the current passing through the transistor. Current passing through the transistor, which is nothing but the collector current. Means how much input current is there, same is getting out. Okay, means we are having the IE equals to the IB plus IC. We are having one equation called as IE equals to the IB plus IC. So if you want, I can write this one. IE, it should be very suffix, but I'm just writing it as a IE. Yeah, so I'll go with the short. IE equals to the, if you are aware of the transistor, then you will come to know this one. IE equals to the IB plus IC. IB plus IC. Okay, but if this one is a very small value, we used to get in the ideal characteristics says that IB is having the very small current. Current passing through the IB is very small. Then I can say that IE is approximately equals to the IC. IE is approximately equals to the IC means how much current is entering into the diode, the same current is leaving from the diode. So the current passing through the same current is leaving from the transistor, not the diode. I'm sorry. So how much current is entering into the transistor? Same current is leaving from the transistor. Because I is approximately equals to the IC. Okay. Now, as we know that the current passing through this particular diode transistor is nothing but the collector current, whose equation is the collector current equation is IC is equals to the alpha n into IS of e to the power of QVE by KT minus 1. QVE by KT minus 1. Similar to the previous equation only, except that we are having one extra term which is called as a forward current transfer ratio. Actually, it is a current gain. In simple format, I can say that in the common base configuration, we have the equation called as a current gain equation, which is nothing but the alpha equals to the output by input, which is the IC by IB. Okay, IC by IE. Okay, so we need to bother about that equations, all those things. Only the thing is, this is the final equation of the current passing through the diode. Current passing through the transistor. So the terms are alpha n is nothing but the forward current transfer ratio. IS is nothing but the emitter saturation current. This current is a emitter saturation current. Na? This emitter saturation current is a current due to the minority charge carriers. This is a current due to the minority charge carriers. Okay, now remember this point. IS is nothing but it is a emitter saturation current which is due to the minority charge carriers, not due to the majority charge carriers. And here we are having the that is a e power QVE by KT minus 1. So Q is the electron charge, K is nothing but the Boltzmann constant, T is nothing but the absolute temperature, V is nothing but what? It is a base emitter voltage. Okay, now so it is a voltage drop between the emitter base voltage. So it is a voltage drop between the emitter base terminals. So I'm assuming this one is a positive, obviously this one is a negative, and this voltage is nothing but the VE voltage. This voltage is nothing but the VE voltage. Are we clear? Okay, so V is nothing but the base emitter voltage. Now again, in the previous case what we made over here, same thing, I would like to do some mathematical calculations. Okay, now so this is the equation number 3 now. So in the next slide I'm taking from the equation number 3. I'm just going with the mathematical calculation. We are having the IC is equals to the alpha n IES of e to the power of QV by KT minus 1. QV by KT minus 1 now. So let me go back to the previous slide. So if you see over here, so here I'm assuming that this particular term is more greater than the 1. For simplifying the equation, I'm assuming like that. So this particular term is more greater than the 1. So when it is more greater than the 1, then if you are subtracting a 1 value from this particular more value, then it is not affecting that much. Okay, now so that's why I'm rounding up this particular terms, this particular part as a e power QV by KT. It is a mathematical assumption only. Okay, nice. So I'm just rounding that one to the e power QV by KT. Okay, so here from the equation number 3, I just cross multiplied and which means I brought the alpha and IES to the left side of the equation. So this is what we are having, and I'm rewriting the same equation like this. So here you can bring this exponential to the right side. Now when you bring the exponential to the right side, obviously it is converted into the log format. QVE by KT, it is a mathematical way of explanation. So we list about how exactly it is coming, all those things. Okay, now if we start that one, then it is not going to be the physics class, it is going to be the mathematical class. Okay, now it is not like that. Okay, so QVE by KT, which is equals to log natural, and finally we are having the VE KT by Q log natural IC by IES minus log natural alpha n, because we are having the alpha n. So alpha n it is a log natural. So here I'm assuming these two as a one term because it is a gain. Because when we are taking the output by input, then obviously it is a current gain. We call that one as a current ratio. Simply, if you are not interested to use the word gain, simply you can take it as a current ratio. So I'm assuming this one as a current ratio, as obviously this one is also the gain, as you know this one, right? So this one is also the gain. Okay, so here I'm assuming this term, and this is another term, log natural of if I'm assuming this is a one term, m by n is nothing but the log of m minus log of n, means log natural m minus log natural n. Okay, so based on that factor, so I'll log KT by Q means I brought the KT over here to the right side, which is a KT by Q into log natural IC by IES minus log natural alpha n. Okay, now log natural alpha n. But we know that alpha n is nothing but what? It is a current ratio. It is a current gain, actually forward current ratio. So which is almost equals to the 0, approximately equals to 0. We used to get that one as a 95%, means 0.95, 0.99 or 0.95, like that. We are having the value for the alpha n, which is a forward current gain ratio. Current gain, actually it is a current gain in the common base configuration. In the common base configuration, alpha n is nothing but the current gain, which is approximately equals to the 0. So sorry, approximately equals to the 1. So when it is approximately equals to the 1, then log natural of this one becomes a 0. Okay, now log natural of this one becomes a 0. Then the output voltage, this V is nothing but it is the output voltage. V is nothing but the output voltage, because how much voltage is there between these two terminals? Sorry, how much voltage is there between these two? Same voltage is appearing over here, as I told you in the previous explanation. During this case, how much voltage is there means the ideal characteristics of the diode. How much voltage drop is there right over here? Because of this configuration, same voltage is appearing as an output voltage. So here also same thing. Same voltage is appear as an output voltage. Okay, now same voltage is appear as an output voltage. But we know that IES is nothing but what? It is a reverse saturation current. and this reverse saturation current is a current due to the minority charge carriers. Current due to the minority charge carriers. But we know that the minority charge carriers are getting increased. Means the current due to the minority charge carriers will increase when there is a variation in the temperature. Means if there is a variation in the temperature, obviously the number of minority charge carriers are increasing. So when the minority charge carriers are increasing, obviously the current due to the minority charge carriers is also going to be increase. It is also increase. But here are some way the whatever the reverse saturation current which is there due to the minority charge carriers, it is not almost equals to the it is not equals to the means it is not comparable with the majority charge carriers current. Okay, it is not comparable to the majority charge carriers. Okay, so because of that, the IN is more greater than the IES. So means IN is more greater than the IES. Why I am taking the IN? Because how much current is there at this particular terminal, at this junction, as again same explanation. Current is not entering into the inverting terminal of the op amp. It is actually coming to this one. Means IC is equals to the IN. IC equals to the IN. Because of that, so I am assuming the IC as a IN. And this particular IN is more greater than the IES. IES is nothing but what? Reverse saturation current. IES is nothing but the reverse saturation current, which is due to the minority charge carriers, and this particular current depends on the temperature. This particular current depends on the temperature, but the minority charge carriers current is always less than the majority charge carriers current. So majority charge carriers current is nothing but the IN. Okay, so majority charge carriers current is nothing but the IN. Okay, so here I am assuming this IN is nothing but what, ma? Again, don't get confused. IN equals to the IC. Go back to the previous diagram. So go back to the previous diagram. You can see that one IC equals to the IN. So here IN is more greater than the IES, and the alpha n is nearly equals to the 1. So obviously it becomes a 0, and this factor IN is more greater than the IES now. So if you see this equation, what is the main intention of this equation is, if you see this equation, the output voltage is there in terms of the log, because this factor will get nullified because it is approximately equals to the 1, means I can make it as a 1. Finally, mathematically it becomes a 0. Okay, so it is a log natural IC by IES. So the output voltage, whatever the output voltage which we are having, it is there in terms of the log format. Well and good. But the drawback of this particular equation is, whatever the IES we are having, which is a temperature dependent one, If at all the temperature of the environment where we are using the transistor, that is a logarithmic amplifier, is getting changed, means increasing, then obviously this factor will get affected more. Means in this particular equation, we have the temperature dependent term. Means whenever there is a variation in the temperature, obviously this value get changed. But we are not interested to see the output output depends on the temperature, variation in the temperature. Okay, now, so to avoid that one, instead of using one transistor as a diode, which is called as a trans diode, instead of using one trans diode, I am going with the dual trans diode. Okay, now, why we are going with the dual trans diodes means, it is just because of IES depending on the temperature. IES value depends on the temperature. Are we clear? So that diagram means the dual transistor diagram looks like this. Okay, now this is a dual transistor. Transistors which are used as a diodes in logarithmic amplifier. This is a practical logarithmic amplifier. I am assuming that EI is a voltage which is applied as an input to this particular amplifier, and we are having the this particular EI, and R1 is there. Q1, Q2 transistors are acting as a two trans diodes, and here the current passing through the Q1, how much current is passing through this particular Q1, that is decided by the EI and R1, and how much current is passing through this particular Q2, that is decided by the VZ, this particular voltage. Here I am using the Z0 diode. So the current passing through this particular Q2 decided by the transistor Q3. Okay, now, so transistor Q3 means how much voltage. Here we are using the diode. What is that? GNR diode. Now here we are using the GNR diode. So GNR diode is in the forward bias, it is acting as a normal diode, but in the reverse bias, it is acting as a that is a stabilizer. Okay, now in reverse bias, mainly the Zener diodes are used in the reverse bias, not in the forward bias, because in order to avoid the fluctuations in the current, means in stabilizers we are using the Zener diode, but we are not interested to elaborate the explanation related to the Zener diode. Okay, now simply the Zener diodes are especially used in the stabilizer to stabilize the voltage. Whenever the voltage is crossing certain level, then the Zener diode will get open, and if it is not crossing that level, then it is there in the short format only, means it is giving the constant output voltage. Okay, in the what is that, wherever we are having the stabilizer, there we are using the Zener diodes only mostly. Okay, so here the current passing through the Q2 decided by this particular factor. Whatever the elements we are having, this is the factor, this factor and this voltage is deciding how much current is passing through this particular Q2. Okay, now we are taking the output across this particular terminal now. Okay, the output at the E0 is decided by the Q1 now. The output at the E0 is decided by the Q1, and R2 value. Okay, now so R2 value is chosen. Sorry, it is a R2. It is not the R2. It is a RT. R suffix T. Okay, so yeah, RT value is chosen in such a way that the voltage drop across this one, whatever the voltage drop which is there across this particular RT value, should be equals to the voltage difference between the VBE voltage of the Q1 transistor and the VBE voltage of the Q2 transistor. We have taken the VBE voltage as a VE. Okay, if you want, I'll go back to the previous slide. So here we are having the VE. VE is nothing but the, I think I may have written that one. Yeah, V is nothing but the emitter base voltage. Okay, emitter base voltage. So if you see this one, the voltage drop across the RT is nothing but it is a, which is equals to the voltage drop across the RT is equals to the voltage drop across the base emitter voltage, that is the emitter base voltage of this particular Q1, that is a, and the emitter base voltage of this particular Q2. Or I can say that voltage drop across the RT is nothing but it is a potential difference between the, or voltage difference between the voltage drop across the base emitter voltage of this particular Q1 and base emitter terminals of this particular Q2. Okay, so means if I am assuming it as a VBE1 and VBE2, then the voltage drop across this one is nothing but the VBE1 minus VBE2. Okay, so like that it is decided. Okay, now the output voltage E0 is decided by the A1. The output voltage E0 is decided by the A1. Okay, now let us see how much current is passing through this particular Q1. I told you that the current passing through the Q1 transistor will be decided by the input voltage and the R1 resistor. As we know that if you take this one, so see here we are having the input voltage and the resistor. Now I am assuming that because of this combination, I am assuming that the current passing through this one is a capital I. The current passing through this one is a capital I. Okay, from this particular term. But we know that there is no current passing through this end, this terminal, because it is at the ground position. Because we are having the virtual ground property. Now, how much voltage is there at the non-inverting terminal? Same voltage is there at the inverting terminal. It is a basic property of the operation amplifier. Okay. So here it is a ground, and means over here we are having the ground. Then the current passing through this particular resistor is nothing but the actually it is a EI minus 0 by R1. If we are taking the formula, exact formula, or in simple format, we can say that it is a EI by R1. EI by R1 is nothing but it is a current passing through this particular resistor. Why it is a EI by R1? Because it is in the ground position. This terminal is in the ground position. So it is a EI by R1 and okay, EI by R1. No need to take the complete explanation. So how much current? I am assuming this current is a I. So the same current will be passing through this particular Q1 transistor. Okay, so current passing through the Q2 decided by these factors. Na? So there is nothing but the IR is equals to the VZ1 by R3. IR equals to VZ1 by R3 means the current passing through the Q2 is nothing but the current which is coming from the Q3 transistor. So as we know that in ideal characteristics we can replace the diode in the forward bias we can replace the diode in the forward bias with short circuit. In the reverse bias it is in the open circuit, but the positive terminal is connected to the anode of the diode. That's why I am replacing this one with the short circuit. Now How much voltage drop is there across the resistor R3 is nothing but the voltage drop, that is the Zener voltage. The voltage drop across the Zener diode, because both are in the parallel. How much voltage is appearing over here? Same voltage will get appear across the resistor R3. Because of that, the current passing through this one is nothing but VZ1 by R3. VZ1 is nothing but it is a Zener voltage. It is a Zener voltage in the reverse bias. Zener voltage in the reverse bias. Are we clear? So Zener voltage in the reverse bias. Then the current passing through this particular Q2 is nothing but the IR equals to the VZ1 by R3. IR equals to VZ1 by R3. Let us suppose. So as I told you that the current is a I in, I assumed it as a in I, but it is a I in current. So as per the slide, it is a I in current, right? So this is the I in current. I in current is nothing but the EI by R1 ma. Actually, it is the R1. It is not the Ri ma. It is the R1. It is the R1 because this resistor is R1 only, right? This is the R1, not the Ri. So it is the R1. So cut and paste. So unfortunately, I forgot to change this one as a 1. Okay, it is a cut and paste. That's why we have the EI by R. Actually, it is the EI by R1 flows through the Q1. So output voltage is controlled by the A1, and RT is nothing but it is a that is the voltage across the RT is equals to the difference between the, that is a voltage difference. Yeah, voltage difference means difference between the VB of the Q1 and the Q2. Okay, VB of the Q1 and the Q2. As we know that at 25 degrees Celsius, by substituting the absolute by substituting the K value, Q value, and this particular temperature over here, this term KT by Q reduced to the 0.0257 millivolts. 0.0257 millivolts. Okay. So if the ratio between, we are taking the ratio, if the ratio between the R2 to RT is R2 by RT is equals to the 15.9, then what is the output voltage of this particular logarithmic amplifier, where we are using the dual trans diodes to give the logarithmic output. Okay, now to give the logarithmic output. So this is what we are having. E0 is equals to the minus K log. Oh, I'm sorry. Actually, only one log should be there. Wait a minute. Let me change this one. It is a log based trend, right? Oops. Wait a minute. No, only one log should be there. I just gone with cut and paste. Okay, so this is what the output voltage. This is the output voltage at this terminal E0. Okay, so let me go back to that. So this is the output voltage. IN by IR equals to the E0 equals to the minus K log base 10. In by IR equals to the minus K log base 10, means in terms of the current and in terms of the voltage. Okay, so whatever the factors which we are introduced over here, those factors, capital K is nothing but the 1 plus R2 by RT of KT by Q into log natural 10. Okay, now VR is nothing but the VZ1 by VZ1 into R1 by R3. It is a potential. This is a voltage. Okay, now VR is nothing but the voltage. VR equals to the VZ1 into R1 by R3, and finally we are getting the output like this. If you are fixing the R3 value as a R1 VZ1, then the output voltage of our logarithmic amplifier is minus log of input voltage AI, minus log base 10 of EI. So finally the conclusion for this one is, we have seen the output of a particular operational amplifier or a particular amplifier in terms of the log. So that's why the means if you are seeing the output voltage or output current in terms of the current equations in terms of the log format, then we can say that those amplifiers are the logarithmic amplifier. The main intention of the logarithmic amplifier is to see the output in terms of the log format. We are making use of the logarithmic amplifier. If you see this one, the output voltage E0 equals to the log of EI. I'm not considering all the factors. It is a log of EI. Okay. So this is all about your logarithmic amplifier. Okay, if you are having any queries regarding this particular topic, let me know in the group, or you can comment in the comment section. Okay, that's all for today's class. We'll continue in the next class.